In 2011, CERN shook the entire world of physics. Scientists announced that neutrinos, ghostly particles that pass through solid matter almost undetected, appeared to be traveling faster than light. If true, everything changes. Every equation, every law, every assumption about how the universe works. For months, scientists checked their data over and over, terrified of what it meant. If particles could outrun light, causality itself would collapse. The principle that cause comes before effect. Gone. Time travel, paradoxes, physics as we know it, collapsing. Eventually, they traced the problem to a loose fiber optic cable. The anomaly vanished. But those few months, scientists stared into the abyss of rewriting everything we thought we knew about reality. And even the physicists admitted it. That was kind of terrifying, and that was just a cable. Imagine what happens when the experiments actually work. If you enjoy what you are about to hear, consider subscribing. It helps more than you know. We are going inside the machine. We are going back to the first second of time. Take a breath. We start now. There is a theory spreading across the internet that CERN is not just smashing particles, that it is breaking something far more fragile, reality itself. Millions of people believe it. Engineers, teachers, nurses, ordinary people who woke up one day and felt, with absolute certainty, that something about the world had quietly shifted, that a memory they held clearly, confidently, in vivid detail, was now wrong, officially wrong, provably wrong, and they cannot explain it. This phenomenon has a name, the Mandela effect. It started with Nelson Mandela. A significant number of people remember him dying in prison in the 1980s. They remember the news coverage. They remember his funeral. Some even remember his widow's speech. But Mandela did not die in prison. He was released in 1990, became president of South Africa, and died in 2013. The memory millions carried was simply not real. That should have been the end of it. A strange case of collective false memory, filed away and forgotten. But it was not the end. It was the beginning, because people started comparing notes, and the list kept growing. A famous children's book series that millions remember as the Berenstain Bears, spelled B-E-I-N, is actually spelled B-E-R-E-N. A movie called Shazam, starring a famous comedian in the 1990s, that people remember watching, rewinding, quoting, never existed. A line from one of the most iconic films ever made, one almost everyone can recite, is remembered differently from what the recording actually says. These are detailed, confident, shared memories, held by people who have never met each other across different countries, different generations. And then, someone asked the question that changed everything. When did these memories start shifting? The timeline, for many people, pointed to 2008, the year CERN's Large Hadron Collider first powered on. The theory, stated plainly, is this. CERN's experiments are so powerful, so fundamentally disruptive at the quantum level, that they are punching holes between parallel timelines, sliding our reality into an adjacent version of itself, a version where the spelling is different, where the movie never got made, where a man died in a different decade, and we arrived here with our old memories still intact, like luggage from a world that no longer exists. It sounds like science fiction, and that is exactly what makes it so hard to dismiss for the people who believe it. Because here is what is confirmed, not theory. CERN does study the fundamental structure of reality. CERN does explore whether extra dimensions exist. CERN has produced results that physicists themselves cannot fully explain. Peer-reviewed, publicly documented facts. So, when someone says CERN might be bending something we do not understand, they are not entirely wrong to wonder. They are just wrong about what it actually means. The science does not support timeline shifts. What it does support is stranger in its own way. The universe, at its smallest scales, behaves in ways that violate every instinct a human brain has developed over hundreds of thousands of years. Particles exist in two states at once. Outcomes change based on observation. Reality at the quantum level is not a fixed thing you can point to and say, "This is what is real." The Mandela effect taps into something genuine, a real unease, a real suspicion that the ground beneath physics is not as solid as textbooks suggest. And the unsettling part? The physicists at CERN would not entirely disagree with that last sentence, but what they have actually found inside that collider goes far beyond shifted memories and misremembered names. What they found was something that should not exist at all. Most people picture CERN as a laboratory: white coats, computer screens, coffee-stained notebooks covered in equations. That picture is not wrong, it is just massively, almost laughably, incomplete. CERN is a machine built to answer the oldest question a human being can ask. Where did everything come from? Physically, scientifically, with numbers, measurements, and repeatable results. The Large Hadron Collider sits beneath the Swiss and French countryside, buried roughly 300 feet underground. It is a ring, a perfect engineered circle, 17 miles across. If you tried to walk it, it would take 5 to 6 hours at a steady pace, so large that engineers had to account for the curvature of the Earth when they built it. Inside that ring, two beams of protons travel in opposite directions. They accelerate to 99.99999% the speed of light. At that speed, a single proton completes the entire 17-mile loop 11,000 times per second. Let that settle for a moment. 11,000 laps per second. The magnets that steer those beams operate at minus 456 degrees Fahrenheit, colder than the vacuum of deep space. CERN has created one of the coldest places in the known universe, right beneath farmland on the border of two countries, to keep particles on a straight enough path to collide, and then it makes them collide. The energy released in those collisions, focused into a space smaller than an atom, briefly reaches temperatures 100,000 times hotter than the core of our star. For a fraction of a second, in a tunnel under Europe, conditions exist that have not existed anywhere in the universe since the first microseconds after the Big Bang. This is confirmed, not a theory. It is what the machine does. Now, here is where physicists start to look a little less comfortable. When you recreate the conditions of the Big Bang, even briefly, even at microscopic scale, you are not just studying the past. You are, in a measurable sense, reproducing it. You are asking the universe to show you its own birth certificate, and the universe does not hand that over quietly. The data coming out of these collisions has challenged assumptions physicists spent decades treating as settled. Particles that behave wrong, symmetries that break when they should not, patterns that fit no known model. One researcher, speaking at a conference in 2017, described certain results as, and this is confirmed, keeping him up at night. This is not a machine that politely confirms what we already know. It is a machine that keeps finding things we do not. And the people running it are not scared in the way that conspiracy theories suggest. They are scared in a different, quieter, more professional way. The way you feel when you pull back a curtain and realize the room behind it is much bigger than the building you are standing in. CERN does not unsettle physicists because it might break the world. It unsettles them because it keeps suggesting the world is something entirely different from what they thought. And the first time, it truly proved that it did so with a particle hiding inside every atom of your body since the beginning of time. Before anything collides, before any discovery is made, something almost impossible has to happen first. A proton has to be convinced to travel in a circle. This sounds simple. It is not. A proton carries an electric charge, travels at nearly the speed of light, and left to itself would shoot in a straight line until the end of time. To bend its path, you need a magnetic field of almost incomprehensible strength. And to sustain that field around 17 miles of tunnel, you need one of the most sophisticated engineering systems ever constructed by human hands. The Large Hadron Collider uses 9,600 superconducting magnets. Each one is roughly 50 feet long. Together, they form an unbroken chain around the entire ring, each one precisely aligned to within fractions of a millimeter. If any single magnet drifts even slightly out of position, the beam veers off course and the experiment fails. To make the magnets work, they are cooled using liquid helium to minus 456 degrees Fahrenheit. At that temperature, electrical resistance disappears entirely. Current flows through the magnets with zero loss, generating fields powerful enough to bend the path of particles moving at nearly the speed of light. This is confirmed technology, proven, operational, and still almost unbelievable when you hold it in your mind. Before protons even enter the main ring, they go through a series of smaller accelerators, each one pushing them faster, handing them off to the next like runners in a relay race. By the time they reach the main ring itself, they are already moving at a significant fraction of light speed. The ring pushes them further, tighter, faster, until they reach that number, 99.99999%. At that speed, something strange happens that has nothing to do with engineering. It has to do with physics. Time slows down for the proton. This is Einstein's theory of special relativity, confirmed in experiments decades ago. An object moving close to the speed of light experiences time at a different rate than a stationary observer. From the proton's perspective, the journey around the ring takes almost no time at all. From the perspective of the physicists watching, it completes 11,000 loops per second. Two beams run simultaneously in opposite directions, brought together only at 4 specific points around the ring. At those points, the beams cross, and protons meet head-on at a combined energy that briefly tears open the fabric of the particle world. The engineers who built this machine spent decades on it. They solved problems that had never been solved before. They aligned magnets over 17 miles to within a hair's width. And after all of that extraordinary precision, what they built is essentially a place where two tiny things crash into each other. The simplicity of that collision hides everything that makes it extraordinary. Because when those protons meet, they do not just break apart. They briefly become something the universe has not seen in 14 billion years. Two protons meet. It takes less time than any clock ever built can detect. And in that immeasurable sliver of existence, something happens that rewrites what we understood about the beginning of everything. Protons are not like billiard balls that crack apart on impact. They are more like tiny, seething clouds of smaller things, quarks and gluons, bound together by forces so strong that isolating a single quark would require more energy than exists in the observable universe. When two protons collide at near light speed, those clouds overlap and interact in ways that are fundamentally chaotic. The energy of the collision does not just scatter particles, it creates them. Out of pure energy, in the instant after impact, new particles flash into existence. Particles that have not existed freely in the universe since the first millionth of a second after the Big Bang. This is confirmed. It is what Einstein's most famous equation tells us. Energy and mass are interchangeable. Pour enough energy into a small enough space, and matter appears. Physically, measurably, the temperature inside that collision point reaches 4 trillion degrees Fahrenheit. The core of our star sits at around 27 million degrees. The collision point inside the Large Hadron Collider is roughly 100,000 times hotter than that. It is the hottest thing human beings have ever deliberately created. For a fraction of a second, the conditions that existed in the universe when it was less than 1 microsecond old are reproduced inside a chamber not much larger than a refrigerator. This is where the fear begins to make more sense. Recreating the Big Bang, even at microscopic scale, is not a neutral act. It is an act of radical intrusion into the most fundamental level of physical reality, and physicists are the first to acknowledge that what comes out of those collisions is not always what the models predicted. The detectors surrounding each collision point, machines the size of apartment buildings, record every particle that emerges. They generate more data per second than all of the world's internet traffic combined. And even then, they have to throw most of it away because no system could store or process it all. What they keep are the events that look unusual, the collisions where something unexpected happened, where a particle appeared that the equation said should not be there, or where a particle that should have appeared did not. Those unusual events are where the real science lives. Here is what physicists believe, though it remains in the territory of theory. In the first moments after the Big Bang, the universe was filled with a state of matter that no longer exists anywhere in nature. A primordial soup of quarks and gluons, unbound, free-moving, impossibly hot. They call it quark-gluon plasma, and the Large Hadron Collider has recreated it. That is a published, peer-reviewed result, and it raises a question nobody has fully answered yet. When you put the universe back in the state it was at its very beginning, do the rules that govern it now still apply? The answer is not entirely yes. On the 4th of July, 2012, something happened in a conference room at CERN that made grown physicists cry. From relief, for nearly 50 years, the most important particle in physics had been a prediction without a proof, a mathematical ghost, something the equations demanded must exist, but that no experiment had ever directly confirmed. Its absence was an embarrassing crack in the foundation of the entire Standard Model, the theory that describes every known particle and force in the universe. That crack closed on the 4th of July, 2012. The Higgs boson had been found. To understand why this matters, you need to forget almost everything your intuition tells you about mass. You probably think of mass as a property things have. A rock is heavy because it has mass. Mass feels like something inherent, baked into objects from the beginning. It is not. Mass, for fundamental particles, is something they acquire. They do not start with it. They gain it through interaction with the Higgs field, an invisible field that permeates every cubic inch of space in the observable universe. Every particle that has mass gains that mass by moving through the Higgs field and being slowed by it. The Higgs boson is the particle associated with that field, finding it confirmed that the field is real. Here is the comparison that makes it click. Imagine the Higgs field as a room filled with people at a party. A celebrity walks in and everyone crowds around, slowing them down. That resistance is mass. A more obscure guest walks through and barely anyone notices. They move quickly, almost unimpeded. That guest is something like a neutrino, nearly massless, barely interacting. Everything you are made of, every atom, every proton, every electron, moves through the Higgs field constantly. Every moment of your existence, your mass, is being actively generated by an invisible field that fills all of space. That is confirmed, science, fact. Now here is where it gets uncomfortable. The Higgs boson that CERN found has a mass that sits in a very specific and very suspicious range. Physicists call it the electroweak scale, and that particular mass value places our universe in a state that theorists describe as metastable. Metastable means stable, but only for now, only for as long as nothing disturbs it. The implications of that word will come back later in this story, and when they do, they will be significantly more unsettling than anything a false memory or a shifted timeline could ever suggest. The Higgs discovery was a triumph, one of the greatest in the history of science. A decades-long hunt ended, a fundamental truth confirmed, but the number they measured when they found it opened a door that no one had been fully prepared to walk through. And on the other side of that door was a question so large, so quietly terrifying that it changes the meaning of the word existence. 85% of the universe is missing. The math demands it must be there. The effects of it are visible everywhere. And yet, every instrument ever built has failed to detect a single particle of it directly. This is the consensus position of modern cosmology, supported by decades of independent observations from different teams using different methods on different continents. The universe we can see, every galaxy, every star, every atom of gas and dust, makes up only about 15% of all the matter that must exist based on how gravity behaves at large scales. The rest is dark matter, and CERN is hunting it. Here is what makes dark matter so strange. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation of any kind, which means it is invisible to every telescope, every detector, every sensor ever built to observe the universe. It passes through ordinary matter almost without effect. Right now, billions of dark matter particles may be passing through your body every second, and you would never feel a thing. What we do know is confirmed through its gravitational effects. Galaxies rotate at speeds that make no sense given the visible matter they contain. If you calculated the mass of a galaxy from the stars and gas, you can see and then use that mass to predict how fast the outer edges should rotate. You would get the wrong answer by a significant margin. The outer edges rotate far too fast. Something invisible is providing additional gravitational pull, something that outweighs all visible matter in the galaxy by a factor of roughly 5 to 1. That something is dark matter. It forms a vast cosmic web, a scaffolding of invisible structure stretching across billions of light years, along which all the visible matter in the universe is arranged. Every galaxy cluster, every galactic filament, every structure in the observable universe sits along threads of dark matter like water droplets on a spider web, and we have never touched a single thread. CERN's search for dark matter is one of the primary goals of current experiments. The most promising candidates are particles that interact only through gravity and the weak nuclear force. This is still theory, not confirmed. If true, the Large Hadron Collider's collisions might produce them. So far, they have not appeared. Every predicted mass range has been tested. Each result has come back empty. Dark matter might not be made of any particle type the standard model has room for. It might require entirely new physics. Physics that does not yet exist in any textbook. Physics that CERN is, whether it intends to or not, slowly forcing into existence by ruling out everything else. Something is out there holding the universe together. Something that has shaped every structure in existence for 14 billion years. And we still have no idea what it is. But what follows is even more unsettling. Because dark matter is invisible. What CERN has found in its search for antimatter has the potential to be something far more dangerous. Every particle that exists has a twin. An identical twin in almost every way. Same mass, same spin, same fundamental properties, but with one crucial difference. Opposite charge, opposite quantum numbers. A perfect mirror image of the original particle. This twin is called an antiparticle, and when matter and antimatter meet, they do not bounce off each other. They do not coexist. They annihilate. Both particles vanish in an instant and are replaced entirely by pure, explosive energy released according to Einstein's equation. The annihilation is total, 100% efficient, no waste, no byproduct, no residue, just energy. For comparison, a nuclear bomb converts less than 1% of its mass into energy. Matter-antimatter annihilation converts 100%. The energy released by annihilating a single gram of antimatter with a single gram of matter would be equivalent to a nuclear explosion, roughly 40 times more powerful than the bomb dropped on Hiroshima. 1 gram. CERN produces antimatter. The total amount of antihydrogen ever created at CERN could not power a light bulb for more than a fraction of a second. But the principle is established, confirmed, and reproducible. Antimatter is real. It is created in colliders regularly. It is briefly held in magnetic traps, specifically designed to prevent it from touching the walls of its container, because the instant it does, both the antimatter and the container material vanish in a flash of gamma rays. This raises a question that sounds almost too large to ask. Where is all the antimatter? The Big Bang should have produced equal amounts of matter and antimatter. If the universe began in perfect symmetry, the newborn universe contained an identical number of particles and antiparticles. They should have found each other. They should have annihilated each other completely, leaving behind a universe of pure energy with no matter, no stars, no planets, no life, and yet here you are. Something, at some point in the first seconds of the universe, gave matter a tiny advantage, a fractional preference. One extra particle of matter for every billion particle-antiparticle pairs, the rest annihilated. And that 1 in a billion survivor, multiplied across the entire universe, became everything, every mountain, every ocean, every galaxy, every atom in your body. You are the leftover. CERN is attacking this mystery directly through a dedicated experiment studying anti-hydrogen atoms held in magnetic traps. Scientists have succeeded in creating and holding them with increasing precision, comparing their properties to regular hydrogen with instruments more sensitive than anything previously built. So far, anti-hydrogen looks frustratingly identical to hydrogen. Every measurement has come back symmetrical. No difference found, which means either the instruments are not yet sensitive enough, or the asymmetry lies somewhere even deeper, in physics that the standard model does not yet contain, or the question of why matter 1 is even stranger than anyone has supposed. And there is one line of experiment at CERN pushing into territory that's strange and further still. Let's stay with that 1 in a billion number for a moment, because it is worth feeling the full weight of it. In the first second after the Big Bang, the universe was a fireball of pure energy. As it cooled, that energy condensed into particles. For every billion antiparticles, there were 1 billion and 1 particles of matter. The billion pairs found each other and annihilated. The one left over survived, 1 in a billion. If that ratio had been exactly even, the universe would have ended in its first second. Total annihilation. A universe of light with nothing in it. No matter, no structure, no time unfolding into anything meaningful. If the imbalance had been larger, if matter had a stronger advantage, the physics would shift, the forces would balance differently. Stars might not form, chemistry might not work, life might be structurally impossible. The 1 in a billion imbalance sits in a range that permits a universe like ours. This is confirmed. What is not confirmed is why. The technical name for this asymmetry is CP violation. C stands for charge conjugation, essentially swapping matter for antimatter. P stands for parity, flipping the spatial coordinates, like holding the universe up to a mirror. CP violation means the universe does not behave the same way when you perform both of those operations simultaneously. In plain language, the laws of physics treat matter and antimatter slightly differently, in ways that are subtle, specific, and deeply embedded in the mathematics of particle interactions. CP violation was first observed in 1964 in an experiment studying particles called kaons. It was one of the most shocking results in the history of physics. The laws of nature were supposed to be symmetric. Matter and antimatter were supposed to be perfect mirrors of each other. That experiment proved they were not, and the violation measured was far too small to account for the imbalance that allowed the universe to exist. CERN has detected CP violation in a particle called the beauty quark. The measurements are precise. The violation is real. But when physicists add up every known source of CP violation in the standard model, the total is still orders of magnitude not too small to explain why there is a universe at all. There must be more, a source of asymmetry that nobody has found yet, a deeper layer of physics where matter's advantage is encoded, and every time CERN runs and fails to find it in the expected places, the mystery deepens. This is not a comfortable position for science to be in. The fact that you exist, that anything exists, is not yet fully explained by the best theory of matter ever constructed. The universe should not have survived. By the numbers, everything should have cancelled out, and yet 14 billion years later, here we are, wondering why. That question sits at the very edge of what science can currently answer. But there are edges further out than that, places where the questions stop being about particles and start being about the structure of space itself. Some of those questions involve dimensions you cannot see, cannot touch, and cannot rule out. The universe has 3 dimensions of space, left and right, forward and backward, up and down. 3 coordinates needed to locate any point in space. This is so fundamental to human experience that it barely registers as an assumption. It feels like a fact. In physics, it is not a fact. It is an observation, and observations have limits. Several serious, mathematically rigorous theories of physics require more than 3 dimensions of space to work. As a mathematical necessity, the equations simply do not balance without them. String theory requires 10 or 11 dimensions depending on the version. The extra dimensions, in most formulations, are not large open spaces you could walk through. They are curled up, folded in on themselves, compressed to scales so tiny that no current instrument could directly detect them. Dimensions existing at every point in space, invisible because they are smaller than anything we can measure. This is theoretical, but it is serious theory, pursued by serious physicists at serious institutions for decades. Here is where CERN enters the picture. If extra dimensions exist at the scale some theories predict, the collider's collisions might produce effects that leak into them. Specifically, gravity might leak. Of the 4 fundamental forces, gravity, electromagnetism, the strong nuclear force, the weak nuclear force, gravity is by far the weakest. So weak that the gravitational pull of the entire planet Earth can be overcome by a small magnet on a refrigerator door. One explanation, unconfirmed but mathematically serious, is that gravity appears weak because it is spreading across more dimensions than the other forces. The other forces are confined to 3-dimensional space. Gravity leaks into extra dimensions, diluting itself. What we experience is only a fraction of gravity's actual strength. If this is true, certain collision events at CERN should produce a characteristic signature, missing energy, a collision where the inputs and outputs do not balance, where some energy appears to simply vanish into a dimension we cannot detect. Physicists have looked for this signature. So far, no confirmed detection. But the implications, if evidence were ever found, would be staggering. It would mean the universe is not 3-dimensional in any complete sense. It would mean there are directions in space that human beings cannot perceive, cannot access, and have never directly observed, but that are as real as the room you are sitting in. It would mean everything you have ever experienced exists on a kind of thin surface, floating in a vastly larger space. And if that larger space exists, physics has no answer yet for what else might be in it. But there is a more immediate fear that surrounded CERN long before it ever turned on. A fear that went to court, a fear that made international headlines, and it concerned something much smaller than a dimension. Something that some people believed could swallow the Earth. In 2008, a retired nuclear safety officer named Walter Wagner filed a lawsuit in a federal court in Hawaii. His target was CERN. His argument was that the Large Hadron Collider, when activated, could produce microscopic black holes, and that those black holes, rather than evaporating, as theoretical physics predicted, might instead grow, slowly at first, then faster, consuming matter around them, sinking to the center of the Earth, feeding on the planet from the inside out until nothing remained. The lawsuit generated international media coverage. Physicists were asked to respond. CERN issued official safety reports, and the question it raised forced a genuine, public reckoning with what the machine was capable of. So let's take it seriously, the way the scientists themselves did. First, the confirmed part. CERN's collisions can theoretically produce micro black holes. It is a prediction that follows from certain extensions of general relativity combined with extra dimension theories. If gravity is stronger at small scales than standard physics suggests, the energy density of a collision might, in principle, be sufficient to create a microscopic region of extreme space-time curvature. Now here is what the science says happens next. Stephen Hawking's theoretical work, developed in the 1970s, predicted that black holes emit radiation as a consequence of quantum effects near the event horizon. The smaller the black hole, the faster it evaporates. A micro black hole of the kind CERN might theoretically produce would evaporate in an interval of time so short it makes a nanosecond look like an eternity. It would vanish before it could interact with a single additional particle. This is the theoretical consensus, and it is supported by a deeply reassuring piece of additional evidence: cosmic rays. Every second, the Earth is bombarded by particles from space. Some carry energies vastly exceeding anything the Large Hadron Collider can produce. They have been hitting the Earth, the Moon, neutron stars, and white dwarfs for billions of years. If high-energy particle collisions produce dangerous, persistent black holes, those black holes would have swallowed entire astronomical objects long ago. The Moon still exists. Neutron stars still exist. The Earth has absorbed cosmic rays for 4.5 billion years and is still here. The court ruled against Wagner. CERN switched on. The world did not end. But here is what remains genuinely open. Hawking radiation has never been directly observed. It is a theoretical prediction of extraordinary elegance, supported by decades of mathematical work, but it has not been experimentally confirmed. Most physicists consider it almost certainly correct. Almost certainly is not the same as proven. The safety case for CERN is strong, extremely strong, built on multiple independent lines of evidence. And the next danger on the list requires even more precision to understand, because unlike micro black holes, it involves something that does not need to grow, it just needs to touch you. Imagine a particle that converts everything it touches into a copy of itself through pure physics, through the fundamental force that binds the cores of atoms together. Touching it does not infect you. It restructures you. At the subatomic level, instantly, completely, it transforms ordinary matter into something else entirely. This is the theoretical concept behind a strangelet. One of the most unsettling ideas in all of particle physics, not because physicists believe it is likely, but because the mechanism behind it is rooted in real, experimentally confirmed physics. Here is the background. Ordinary matter is made of protons and neutrons. Protons and neutrons are made of quarks. There are 6 types of quarks: up, down, charm, strange, bottom, and top. The protons and neutrons in your body are made almost entirely of up and down quarks. They are the lightest, most stable quark types, which is why ordinary matter is stable. Strange quarks are heavier. They exist in some short-lived particles produced in high-energy collisions and decay almost immediately into lighter quarks. This is confirmed and well understood. The strangelet hypothesis began with a theoretical prediction made in the 1980s. Some physicists proposed that under certain conditions, a chunk of matter containing roughly equal numbers of up, down, and strange quarks, called strange quark matter, might actually be more stable than ordinary nuclear matter. If strange quark matter is more stable than ordinary matter, and if a piece of it ever came into contact with an ordinary atomic nucleus, it might trigger a conversion. The ordinary nucleus, finding the strange quark matter energetically favorable, would rearrange its own quarks and become strange quark matter itself, and the process would continue outward. A single strangelet, if this hypothesis is correct and the strangelet is stable, could theoretically convert the entire Earth into a ball of strange quark matter in a matter of minutes, simply by touching. Now, here is the current state of the evidence. The conversion scenario requires several conditions to be met simultaneously. First, strange quark matter must actually be more stable than ordinary matter. This is unconfirmed. It is a hypothesis. Second, a stable strangelet must be produced in a collision. Experiments at CERN and at the Relativistic Heavy Ion Collider in the United States have specifically searched for stable strangelets in collision products. None have been found, and the cosmic ray argument applies here too. Collisions far more energetic than anything CERN produces happen throughout the universe constantly. Neutron stars, composed of incredibly dense matter and struck by high-energy particles continuously, show no sign of strangelet conversion. They persist. The scientific consensus is that strangelets, in the dangerous form the hypothesis describes, almost certainly do not exist. Almost certainly. That qualifier is not dishonesty. That is physics being precise about what it knows and what it does not know. The next question on that list is not about a particle at all. It is about the state of space itself, about a possibility so quiet, so total, and so difficult to dismiss that physicists gave it a name that sounds almost peaceful. They call it vacuum decay, and it is anything but. The universe might be lying to you. In a precise, physical, mathematical sense, the vacuum of space, the emptiness between particles, the baseline state of reality itself, may not be what it appears. It may be fake. This is called the false vacuum hypothesis, and it follows directly from the mass of the Higgs boson that CERN measured in 2012. The number they found places the universe in a state that physicists describe as metastable. It appears stable, it behaves stably, but the mathematics suggests it may be sitting in a local energy minimum rather than the true lowest energy state. Here is the comparison that makes it imaginable. Picture a ball resting in a shallow dip on the side of a hill. The ball is not moving. From its own perspective, it is perfectly stable. It has no reason to move. But the dip is not the lowest point on the hill. The valley floor far below is lower. The ball is stable only until something nudges it over the edge. Once nudged, it rolls, and it does not stop. The universe may be that ball. If the Higgs field is currently sitting in a false vacuum, a quantum fluctuation could spontaneously kick the field over its energy barrier somewhere in the universe, and from that point, a bubble of true vacuum would expand outward at the speed of light. Inside that bubble, the laws of physics are different. The constants change. The forces balance differently. Atoms as we know them cannot exist. Chemistry cannot exist. Life cannot exist. The bubble expands at the speed of light, which means nothing outside it can see it coming. No warning, no signal. The bubble wall arrives, and the structure of everything within it is fundamentally rewritten. This is confirmed as a theoretical consequence of the Higgs mass measurement. Whether the universe is actually in a false vacuum is not confirmed. The current calculations suggest it is close to the boundary between stable and metastable, close enough that the answer depends on precise values not yet known with sufficient accuracy. CERN's measurements are part of calculating whether the vacuum is stable. More precise measurements of the Higgs boson's properties will help answer that question. If vacuum decay is real, and if it happens, there is nothing that could be done about it. The bubble moves at the speed of light. It cannot be outrun. It cannot be detected in advance. It would arrive without warning and end everything in its path, not with fire or explosion, but with a quiet rewriting of the rules that make existence possible. and CERN did not create this danger. If the vacuum is unstable, it was unstable long before the collider was built, long before humanity existed, long before the Earth formed. What CERN did was measure the number that told us to ask the question. But what comes next is different in character entirely, because while vacuum decay is theoretical, the next chapter is about something that has already happened, something in the data, something no one expected and no one has yet fully explained. Science rarely announces its most important results with fanfare. The headline discoveries, the Higgs boson, the detection of quark-gluon plasma, those get the press conferences, the Nobel Prizes, the front pages. But the results that may ultimately matter most tend to arrive quietly, buried in data tables, flagged in internal memos, discussed in conference rooms where the atmosphere is more confused than celebratory. CERN has had several of these moments, and they matter more than most people realize. The Standard Model of particle physics is the most precisely tested theory in the history of science. Its predictions match experimental measurements to extraordinary accuracy, in some cases to more than 10 decimal places. It is an almost absurdly successful theory, and it is almost certainly incomplete. Physicists have known for decades that it must be incomplete. It has no explanation for dark matter. It cannot account for the matter-antimatter asymmetry that allowed the universe to exist. It does not include gravity in any workable way. It describes 3 of the 4 fundamental forces beautifully and ignores the 4th. These are fundamental structural absences in the best theory we have. So physicists have been searching, in every dataset CERN produces, for cracks, for measurements that deviate from what the Standard Model predicts. Several have appeared. In the decay patterns of particles called B mesons, heavy particles containing a bottom quark, physicists have observed anomalies. The rates at which these particles decay into different products do not match Standard Model predictions with the precision the theory demands. The deviations are small, but they are persistent. They have appeared in multiple independent analyses using different techniques at different times in different countries. This is confirmed. Anomalies exist in the B meson data. Whether they represent new physics or subtle systematic errors in the measurements is still an open question. There have been other unexpected findings, distributions of collision products that peak in unexpected places, ratios between particle types that differ slightly but persistently from theoretical predictions. Events that occur at rates the Standard Model says are impossible, or at rates far below what it predicts. Each one individually could be a statistical fluctuation, a measurement error, an incomplete understanding of a background process. Together, they form a pattern that a growing number of physicists take seriously. The Standard Model is cracking. Under the extreme precision of CERN's measurements, fractures are appearing in a theory that was supposed to be seamless. And one of those fractures has its own name, its own dedicated experimental program, and its own growing army of physicists who believe it is pointing directly at something the Standard Model fundamentally cannot explain. It involves a particle you have almost certainly never heard of, and the way it misbehaves is keeping people up at night. The strangest part is this: every crack in the theory is a crack in our understanding of the ground beneath you. The matter you are made of follows rules that the best theory ever written about matter cannot fully capture, and something out there is responsible for the gap. The muon is not a famous particle. It does not have a dramatic name. It is, in most respects, unremarkable. A heavier version of the electron, unstable, lasting only about 2 microseconds before decaying. It shows up in cosmic ray showers and plays no obvious role in the chemistry of everyday life. But the muon is currently at the center of the most significant potential crack in fundamental physics in decades. The story begins with a property called the magnetic moment. Every charged particle that spins generates a magnetic field. Similar to how a spinning ball of charge becomes a tiny magnet, The strength of that magnetic field, relative to the particle's spin, is called the magnetic moment. For the muon, this value can be calculated with extraordinary precision using the standard model and measured with extraordinary precision in laboratory experiments. If the measured value matches the calculated value, the standard model holds. If it does not, something is missing from the theory. The measurements do not match. The deviation is described using a quantity physicists call G-2, referring to the difference between the measured magnetic moment and the theoretical baseline. For decades, experiments have suggested the muon's magnetic moment is slightly larger than the standard model predicts, by an amount that is both consistent and stubbornly persistent. In 2021, the Muon G-2 experiment at Fermilab in the United States released results confirming earlier measurements with higher precision. The deviation held. The statistical significance reached a level that physicists call highly suggestive, strong enough that dismissing it as coincidence requires real effort. In 2023, further results push the significance higher still. This is confirmed. The muon's magnetic moment does not match the standard model's prediction. The gap is small in absolute terms. In terms of what it implies, it is enormous. The standard model's calculation accounts for every particle and force it knows about. Every virtual particle that briefly flickers into existence near the muon. Every possible interaction, every correction. If the measured value is different, it means something is contributing to the muon's magnetic environment that the standard model does not include. Something is there. Something that interacts with the muon. Something that the best theory of matter ever constructed does not have a name for. CERN is searching for it. Higher energy runs of the Large Hadron Collider are specifically designed to probe the mass ranges where particles capable of explaining the muon anomaly might exist. If they find it, it will be one of the most significant discoveries in the history of physics. If they do not find it in the expected places, the mystery deepens further, into territory where the questions become less about particles and more about the nature of reality at a level so fundamental it barely has language yet. But before we reach that level, there is one more confirmed discovery worth stopping on, because CERN has already recreated something that last existed in the first microsecond of time, something so extreme it has no comparison in the modern universe. For the first microsecond after the Big Bang, the universe was too hot for atoms, too hot for protons, too hot for neutrons, too hot for quarks to bind together into anything at all. The entire universe was a churning, featureless ocean of free quarks and gluons, the fundamental building blocks of matter, unbound, moving freely at temperatures so extreme that the concept of a solid or liquid or gas had no meaning yet. Then the universe cooled. In less than a microsecond, the temperature dropped enough for quarks to bind. Protons and neutrons formed, and quark-gluon plasma, that primordial ocean, disappeared from the universe forever, until CERN brought it back. This is confirmed, published, peer-reviewed. The Large Hadron Collider has recreated quark-gluon plasma in physical reality, inside the ALICE detector, using collisions between lead ions rather than protons. The temperatures reached in these collisions exceed 4 trillion degrees Fahrenheit, conditions that have not existed anywhere in the observable universe since the first moments of time. For a fraction of a second lasting approximately 10 to the power of minus 23 seconds, a timescale so short it makes a billionth of a second look vast, a droplet of primordial matter exists inside the detector, and it behaves strangely. Physicists expected quark-gluon plasma to behave like a gas. At those temperatures, individual quarks should move freely and independently, spreading outward in all directions like steam from a kettle. Instead, it flows like a liquid, the most perfect liquid ever measured. The ratio of its viscosity to its entropy is extraordinarily close to the theoretical minimum that quantum mechanics permits. It flows more perfectly than any substance ever observed in a laboratory, more perfectly than superfluid helium, more perfectly than anything with a comparison point in ordinary physics. This finding was a genuine surprise, a discovery that forced a substantial revision in how physicists model the behavior of matter at extreme temperatures. The equations had to be rewritten, and it raised a question that goes beyond the collider. If the early universe was filled with this liquid, and it was, this is confirmed, then the large-scale structure of the universe that exists today, every galaxy cluster, every cosmic filament, every void, was shaped partly by the fluid dynamics of quark-gluon plasma in the first microsecond of time. The way that liquid sloshed and rippled and expanded affected where matter ended up billions of years later. The structure of the universe you live in was written, in part, by a liquid that existed for less than a microsecond at the beginning of everything, and CERN has recreated that liquid in a tunnel in Switzerland. Something even stranger is hiding in the data from these experiments, though, something that suggests the universe itself may have a preferred direction, a built-in asymmetry that goes deeper than matter and antimatter, an asymmetry embedded in time itself, and that changes the meaning of everything we thought we understood about cause and effect. Physics, for most of its history, assumed the universe was symmetric in time. Run a film of a collision between two particles forward, then backward. The laws governing both should be identical. Both directions should follow the same rules with the same probabilities. This is called time symmetry, or T-symmetry, and it turns out to be broken. In specific particle interactions, the universe behaves differently depending on the direction of time. This is confirmed. It has been measured. The Nobel Prize in Physics was awarded in 1980 for the theoretical framework that predicted it, and experiments since have confirmed it repeatedly. Certain particles, particularly those containing strange and bottom quarks, decay at slightly different rates depending on a combination of properties that encode both the direction of time and the difference between matter and antimatter. When physicists measure these decay rates and compare them against what pure T-symmetry would predict, they find a small but definite deviation. Time is not symmetric at the fundamental level. What does this mean? It means the universe has a built-in preference. The laws of physics are not perfectly reversible. There is something in the mathematics of particle interactions that distinguishes between forward and backward time, not as a result of thermodynamics or statistics, but at a fundamental level that physics has not yet fully explained. This connects to one of the deepest unsolved problems in physics, the arrow of time. We experience time as moving in one direction. Causes precede effects. Coffee cools in a cup. It does not spontaneously reheat. But the fundamental equations of physics at the level of individual particles are mostly time-symmetric. The asymmetry of our everyday experience emerges from statistics, from the enormous number of particles involved, except now we know the laws themselves are not perfectly symmetric either. CERN's Large Hadron Collider beauty experiment has measured T violation in B meson decays with high precision. The results are consistent with the Standard Model's predictions, which is itself a CP violation, the combined matter-antimatter and time reversal asymmetry built into the theory. But here is the thing that should make you pause. The amount of time asymmetry measured is, like the matter-antimatter asymmetry, far too small to explain the arrow of time as we experience it. It is real, it is confirmed, but it points toward a deeper asymmetry that has not yet been found. Somewhere in the structure of the universe, there is a reason that time runs forward, a reason encoded in the physics of particles, and we have found hints of it, but not the source. The deeper we look, the more the universe seems to have preferences we did not know about. Preferences baked into the rules at the most fundamental level, and the framework that should contain the answer to all of this, the theory that describes every known particle and force, is cracking under the pressure of its own precision. The next chapter is about exactly that framework and the uncomfortable truth that the most successful scientific theory ever written is almost certainly wrong. 17 particles, 4 forces, 1 mathematical framework, and a track record of predictive accuracy that no other scientific theory in history has matched. The standard model of particle physics describes everything you are made of and every force that holds you together. The quarks inside every proton and neutron in your body, the electrons orbiting every atom, the photons carrying every electromagnetic interaction, the gluons binding the nuclei of your cells together with a force so strong that releasing it is what powers nuclear weapons. All of it described by 17 particles and their interactions. And it is almost certainly incomplete. Its predictions are extraordinarily accurate, but it is a partial description of a deeper reality not yet reached. A map that is correct within its borders but stops at an edge, with everything beyond that edge labelled unknown. The standard model has no explanation for dark matter. It has no explanation for dark energy, the mysterious force accelerating the expansion of the universe. It cannot account for the observed matter-antimatter asymmetry. It does not include gravity, the most fundamental force in everyday experience. The force that shapes every astronomical structure in the universe does not appear anywhere in the standard model's equations. Physicists have been trying to incorporate gravity into the standard model for decades. Every attempt has either produced infinities, mathematical results that have no physical meaning, or required assumptions that cannot be tested. Gravity, at the quantum level, remains stubbornly incompatible with every other force. The standard model also fails to predict the masses of neutrinos. For decades, it assumed neutrinos were massless. Then experiments confirmed they have mass. The theory had to be patched. It has 17 free parameters, numbers like particle masses and force strengths, that the theory cannot predict from first principles. They must be measured and then inserted into the equations by hand. A theory with 17 unexplained constants is a description waiting for an explanation. And then there is the hierarchy problem. The Higgs boson's mass is 125 times the mass of a proton, but quantum corrections should naturally push the Higgs mass up to an enormously larger value. Getting it to land at the measured value requires a cancellation between contributions of vastly different magnitudes, precise to many decimal places, with no known reason for the cancellation to occur. Physicists call this fine-tuning. Fine-tuning without explanation suggests that something is missing, that a deeper structure exists which would make the cancellation natural rather than miraculous. Finding that structure is one of the central goals of CERN's program. So far, the expected solutions have not appeared. A framework called supersymmetry, which would have solved the hierarchy problem elegantly, has been searched for extensively at the Large Hadron Collider. It has not been found in the mass ranges where it was most expected to appear. The standard model stands, successful, precise, tested to extraordinary accuracy, and resting on foundations that have not been explained. Where does gravity come from? Is there a particle responsible for it? That particle has a name. It has never been detected, and finding it would change physics more dramatically than anything since Einstein. Gravity is the force you feel most directly. Every step you take, every object you pick up, every moment you spend not floating off into space. It is also the force physics understands least. The other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, are described in the standard model by the exchange of particles. Electromagnetism is carried by photons. The strong force is carried by gluons. The weak force is carried by W and Z bosons. Force, at the quantum level, is the result of particles passing back and forth between interacting objects. If this picture is correct for the other three forces, It should be correct for gravity too. There should be a particle that carries gravity. Physicists call it the graviton. The graviton is required to exist if gravity is to be unified with quantum mechanics. Its properties can be predicted. It should be massless, travel at the speed of light, have a spin of 2, and coupled to energy and momentum rather than charge. These are precise predictions, but the graviton has never been detected, and detecting it may be beyond the capability of any instrument humanity could realistically build. Here is why. Gravity is extraordinarily weak at the particle level. A single photon carries enough electromagnetic force to be detected by instruments we have been building for over a century. A single graviton, by contrast, would interact so feebly with any detector that distinguishing it from background noise would require a detector roughly the size of Jupiter, maintained with perfect sensitivity for longer than the current age of the universe. This is a fundamental problem. Gravitons, if they exist, may be permanently beyond the reach of direct detection. CERN's approach is indirect. Physicists look for signatures consistent with graviton exchange, deviations in collision products that would be expected if gravity were being mediated by a particle rather than by smooth space-time curvature. And if extra dimensions exist, gravity might behave differently at short distances, showing up in the data as missing energy. So far, nothing. General relativity, Einstein's theory of gravity, published in 1915, describes gravity not as a force, but as the curvature of space-time. Mass bends space and time around it. The theory is extraordinarily accurate. It predicted gravitational waves, black holes, the bending of light around massive objects, and the precise rate at which clocks run slower in stronger gravitational fields. All confirmed, but general relativity cannot be correct at the quantum scale. At sufficiently small distances and sufficiently high energies, its predictions break down into meaningless infinities. It is a theory of smooth, continuous space-time applied to a universe that, at the smallest scales, is neither smooth nor continuous. Two theories, both confirmed, both extraordinarily accurate in their domains, completely incompatible with each other at the boundary. Something deeper must exist that contains both, and the next chapter ventures into territory where that problem connects to something even more fundamental: the question of what reality actually is when you are not looking at it. Here is an experiment performed, confirmed, and replicated thousands of times in laboratories around the world. Take a single particle, fire it at a barrier with 2 openings. On the other side, place a detector to record where the particle lands. Do not observe which opening the particle goes through. The particle passes through both openings simultaneously. It interferes with itself on the other side, creating a pattern that can only be explained if it traveled through both paths at once. Now, add a detector at the openings to observe which one the particle uses. The particle goes through one opening, only one. The interference pattern disappears. The act of observation has changed the physical outcome. This is the double-slit experiment, performed countless times with electrons, photons, atoms, and even molecules. The result is consistent. The act of measuring which path a particle takes eliminates its ability to travel both paths simultaneously. What does this mean? Physicists have been arguing about it for a century, and no consensus exists on the interpretation. What is agreed upon, what is confirmed, is the experimental result itself. The act of measurement changes the outcome. The universe at the quantum level does not appear to have definite properties until those properties are measured. Before measurement, a particle's position, momentum, and spin exist as a superposition, a combination of all possible values, weighted by probability. Measurement collapses that superposition into a single definite outcome. But the equations that describe the superposition contain no mechanism for collapse. The collapse is something that appears to happen, but the mathematics does not say why, or how, or what triggers it. This is the measurement problem, one of the deepest unresolved questions in physics. The interpretations range widely. The Copenhagen interpretation says the wave function collapse is simply what happens when a quantum system interacts with a classical measuring device. The many worlds interpretation says the wave function never collapses, but every possible outcome occurs in a branching multiverse. Hidden variable theories suggest the apparent randomness masks underlying deterministic variables we cannot access. None of these interpretations has been experimentally ruled out. This is confirmed. We do not know which interpretation of quantum mechanics, if any, is correct. CERN operates entirely within the quantum mechanical framework. The Higgs field, the vacuum state, the structure of space-time, the matter-antimatter asymmetry, the behavior of the muon, all of these are quantum phenomena existing at a level of reality where the act of asking a question changes the answer. CERN is the largest, most precise instrument ever built to ask questions of quantum reality, and quantum reality's answers have consistently surprised the people asking. Something even stranger follows, into territory where the line between serious physics and human mythology has been deliberately blurred by people on both sides. And the real physics, when you look at it carefully, is stranger than either version. The measurement problem leads somewhere deeply uncomfortable. If the act of observation affects quantum outcomes, what counts as a measurement? What is it about the interaction between a particle and a detector that causes the superposition to resolve into a single outcome? Most physicists draw the line at physical interaction. A photon hitting a detector screen, an electron entering a magnetic field, a particle leaving a track in a cloud chamber. These constitute measurements. The observer does not need to be conscious. A camera with nobody watching it still records a definite outcome, but the historical roots of the measurement problem are entangled with consciousness in ways that serious physics has not fully escaped. The physicist John von Neumann, in 1932, formalized quantum mechanics mathematically and argued that the collapse of the wave function propagates backward through every physical system involved in a measurement until it reaches what he called an abstract ego, the conscious observer. His mathematics was impeccable. His interpretation was radical. And it opened a door that some physicists have been trying to close ever since, while others have walked through it. Eugene Wigner, a Nobel laureate, developed the thought experiment now called Wigner's friend. Imagine a physicist inside a laboratory performs a quantum measurement and observes a definite outcome. From inside the lab, the wave function has collapsed. But from outside the lab, if Wigner treats the entire system, physicist, equipment, and particle as a quantum system, the wave function has not collapsed, it is still a superposition, including the physicist's mind. Is there a definite fact about what the physicist inside observed before Wigner himself looks? Extended versions of this thought experiment have been partially realized in the laboratory using entangled particles and quantum memory systems. The results are consistent with the idea that two observers can have mutually contradictory but internally consistent experiences of the same quantum event. This is published, peer-reviewed science. It does not prove consciousness collapses wave functions, but it raises genuine questions about the objectivity of quantum measurements that remain unresolved. CERN probes reality at scales where quantum mechanics is the only framework that works. And at those scales, the questions about what constitutes an observation, what constitutes a definite outcome, and what it means for something to be real before it is measured are not settled. What CERN has confirmed is that the quantum vacuum, the baseline state of empty space, is a seething sea of virtual particles, fluctuating fields, and probabilistic events. Space is not a passive container for matter. It is an active, fluctuating medium that influences everything within it. Whether consciousness plays a role in how that medium resolves into definite reality is a question physics cannot yet answer. The universe at its most fundamental level is contextual, probabilistic, and in some formulations dependent on the act of measurement in ways that have no classical analogue, CERN explores that level of reality more deeply than any other instrument ever built. And one question leads further than all the others, into the numbers themselves, into the precision with which the universe appears to be calibrated, into the terrifying suggestion that existence might not have been an accident. The universe runs on numbers. Physical constants, fixed numerical values that appear in the equations governing every force and every particle, determine what kind of universe exists. The strength of gravity, the mass of the electron, the charge of the proton, the energy of the vacuum, the rate at which the strong nuclear force binds quarks together. These numbers were set at or before the Big Bang, and they have not changed since, and they are suspicious. Change the strength of gravity by a small fraction, and stars either collapse before fusion can begin, or never form at all. Change the mass of the electron slightly, and chemistry as we know it becomes impossible. Alter the strong nuclear force by a few percent, and either no elements heavier than hydrogen can form, or everything fuses into iron almost immediately. Adjust the energy of empty space by even a tiny amount, and the universe either collapses back on itself within seconds, or expands so fast that matter can never clump into galaxies. In every case, the range of values compatible with a universe that allows stars, planets, chemistry, and life is extraordinarily narrow. The constants sit in that narrow range. This is confirmed. The fine-tuning of physical constants is a mathematical observation. Physicists who have no interest in any metaphysical conclusion have calculated these ranges carefully, and the results are not in dispute. What is in dispute is what the fine-tuning means. One interpretation is that it points to a designer, an intelligence that chose the constants to permit life. This is not a scientific interpretation because it cannot be tested. A second interpretation, taken seriously by a large fraction of professional physicists, is the multiverse. If an enormous number of universes exist, perhaps infinitely many, each with different values of the physical constants, then it is not surprising that some of them have constants compatible with life. We find ourselves in one of those simply because we could not have formed in any other kind. The fine-tuning is selection bias. The multiverse is not confirmed. It is a theoretical framework with several different formulations: string theory's landscape, eternal inflation, the many worlds interpretation of quantum mechanics, none of which are currently testable with any instrument that exists or is proposed. A third interpretation is that the constants are not arbitrary but necessary. A deeper theory, not yet discovered, will show that they could not have taken any other values. This is where CERN is most directly relevant. Finding new physics, new particles, new symmetries, new principles could reveal constraints on the constants that make them less arbitrary than they appear. So far, that physics has not appeared. The universe remains suspiciously well configured for existence, with no confirmed explanation for why. Now, let's step inside the machine itself. The physical reality of where all of this is measured, because the scale of what humanity has built to ask these questions is itself a kind of answer. Most of CERN's physics happens in a space smaller than a grain of sand, the collision point, the spot where two protons meet at nearly the speed of light, releasing energy in a flash too small and too brief for any human sense to perceive. Everything, every discovery, every anomaly, every mystery originates in that invisible point, and then CERN builds something the size of a building to read it. The Large Hadron Collider has 4 main detectors. Each one surrounds a collision point designed to catch and identify the particles that fly outward in the microseconds after 2 protons annihilate each other. The largest is called Atlas. It is 46 meters long, 25 meters in diameter, and weighs approximately 7,000 tons. 7,000 tons is roughly the weight of the Eiffel Tower. Atlas is a cylinder of layered detectors, each layer designed to catch a different type of particle. Photons are absorbed in one layer, electrons in another, hadrons, particles made of quarks, in another. Muons, which pass through most matter, are caught in the outermost layer. The second large general-purpose detector is called the compact muon solenoid. Compact is a relative term. It is 15 meters in diameter, 21 meters long, and weighs 14,000 tons, twice the weight of Atlas. At its core sits the world's largest superconducting solenoid magnet, generating a magnetic field roughly 100,000 times stronger than Earth's. This field bends the paths of charged particles as they fly outward, and the degree of bending tells physicists the particles' momentum with extraordinary precision. These two detectors were both used to confirm the Higgs boson. Independent teams, independent instruments, independent analyses, both reaching the same conclusion at the same time. That double confirmation is one of the reasons the discovery was trusted so completely. The other two detectors are more specialized. One is designed for heavy ion collisions and is responsible for the confirmed recreation of quark-gluon plasma. The other is a forward-facing detector optimized for studying particles containing bottom quarks, responsible for the B-meson anomalies and CP violation results discussed in earlier chapters. In a single second of operation, approximately 1 billion proton collisions occur. The detectors record information from every one. The raw data rate is so enormous that CERN employs a layered trigger system, a real-time computer filter that evaluates each collision in microseconds and discards all but the most interesting roughly 1,000 events per second for full recording. 1,000 per second, selected from 1 billion. The rest, gone forever. The events that survive go to CERN's computing grid, a distributed network of computers across the world, collectively processing petabytes of data every year. Physicists on every continent analyze the same datasets, cross-checking each other's results, looking for the same signal through different methods. This is the infrastructure of discovery. Enormous, precise, relentless, and pointing always at the same question. What is reality made of, at the level where it can no longer be divided further? The answers found so far have been extraordinary, and the next step inside the machine itself is stranger than any description of it. 2 protons. They have been accelerating for 20 minutes, round and round the 17-mile ring, 11,000 laps per second, pushed by radio frequency cavities that add energy with every pass, squeezed by magnetic fields to a width finer than a human hair, guided with sub-millimeter precision toward a single point. Now they meet. At the moment of impact, the combined energy of the collision reaches 13.6 trillion electron volts in the most recent runs of the Large Hadron Collider. The protons do not collide as single objects. They are clouds of quarks and gluons, and what actually interacts are individual constituents, one quark from each proton, or a gluon from each, meeting in the center while the rest pass by as spectators. The collision lasts for a duration of approximately 10 to the minus 25 seconds. A nanosecond, 1 billionth of a second, is already beyond human perception. 10 to the minus 25 seconds is 100 billion times shorter than that. In that interval, something violent happens at scales a billion times smaller than an atom. The energy concentrates into a point and begins producing particles. The quarks and gluons, freed briefly by the collision's disruption, recombine almost instantly into new configurations. Hundreds of particles flash into existence per collision. Occasionally, in perhaps one collision in a billion, at the right conditions, something else appears. A Higgs boson, a top quark pair, a Z boson, a W boson. The heavy, unstable particles that reveal the deep structure of the standard model, existing for an interval so brief they travel less than a proton's width before decaying. The Higgs boson exists for approximately 10 to the minus 22 seconds before decaying into other particles, it never reaches the detector. What the detector sees is its decay products, pairs of photons, or 4 leptons, or other combinations. And from those products, physicists reconstruct the mass and properties of the Higgs that briefly existed upstream. Every particle that emerges from the collision point flies outward at a significant fraction of light speed. Within nanoseconds, the first particles reach the innermost layer of the detector, a silicon tracker that records their paths with micron-level precision. A magnetic field bends the paths of charged particles, and from the radius of curvature, the detector determines each particle's momentum. Layer by layer, the particles move outward. Photons stop in the electromagnetic calorimeter, depositing their energy in crystals that scintillate with light. Hadrons are stopped by the hadronic calorimeter, absorbing their energy in alternating layers of steel and plastic. Muons pass through everything and are identified only in the outermost layer by the tracks they leave in gas detectors. In roughly 1 microsecond, it is over. The collision has happened. The data has been filtered and sent to storage, and somewhere in that data, there may be an event that changes physics. Every one of the billions of collisions per second is a question thrown at the universe. Most of the answers are ones we have heard before, but every so often, the universe answers back with something nobody expected. The Large Hadron Collider is the most powerful particle accelerator ever built. It will not hold that title forever. CERN has proposed a successor called the Future Circular Collider, and the comparison to what exists today is almost disorienting. Where the Large Hadron Collider runs in a tunnel 17 miles in circumference, the Future Circular Collider would occupy a tunnel approximately 62 miles in circumference. Built beneath the same Swiss and French countryside, deeper underground, in a ring nearly 4 times as large as its predecessor. The energy it would reach in proton-proton collisions is 100 trillion electron volts. The Large Hadron Collider currently reaches 13.6 trillion. The Future Circular Collider would be roughly 7 times more powerful. The cost is estimated at tens of billions of dollars. The timeline for completion, if approved and funded, would stretch to the middle of this century. This is confirmed as a proposed project with detailed engineering studies completed. It is not yet approved. The decision will involve scientific institutions, governments, and funding bodies across dozens of countries. And it is among the largest scientific investment decisions any generation of humans has ever faced. Why build something so expensive and so large? Because the questions that remain unanswered by the Large Hadron Collider require more energy to probe. The mass ranges where new physics might be hiding, where particles explaining dark matter, or solving the hierarchy problem, or revealing the mechanism behind matter-antimatter asymmetry might exist, extend beyond what the current machine can reach. The Future Circular Collider would also operate in a first phase as an electron-positron collider, a Higgs factory producing millions of Higgs bosons under precisely controlled conditions and measuring their properties to a precision currently impossible. This would sharpen the tests of whether the Higgs behaves exactly as the standard model predicts, or whether deviations betray the presence of deeper physics hidden just beyond current sensitivity. Other projects are proposed elsewhere. A linear electron-positron collider in Japan, a muon collider, a machine that would collide muons rather than protons, offering cleaner collision environments at very high energies because muons, unlike protons, are point-like particles without internal structure. A muon collider at high enough energy could probe mass scales far beyond any current proposal. Each of these machines represents a commitment by the scientific community to a single proposition: that the structure of reality at its most fundamental level is knowable and that the tools to know it are within human reach. There is something almost defiant about it. Faced with a universe that does not give up its secrets easily, the response is to build a bigger machine, to ask the question louder, and the questions being asked have become correspondingly more profound. whether space has more dimensions than 3, whether the vacuum is stable, whether the laws of physics are the only possible laws, or one set among many. These are questions at the very edge of what science can currently frame. And the next discovery, whatever it is, will push that edge further into territory we cannot yet name. Imagine the moment it happens. Somewhere in the data stream of a future collider, an analyst flags an event. The numbers do not fit. The standard model prediction is clear. This collision should produce this signature at this rate. But the rate is wrong, by a margin that, when confirmed across millions of events, represents a genuine deviation. New physics. The room where this is confirmed, in whatever year it happens, will be quiet at first, then loud, then historic. What would it actually mean? The answer depends on what is found, but let's consider the most plausible candidates based on what CERN and other experiments have already suggested. If a new particle is found in the mass range consistent with explaining the muon's anomalous magnetic moment, it would suggest a new force of nature, a fifth fundamental interaction, unknown to physics, operating at scales that have been technically inaccessible until now. The standard model would need extension. New particles would be predicted to accompany the first discovery. If particles consistent with dark matter are produced in collisions, a characteristic missing energy signature appearing in a mass range compatible with weakly interacting massive particles, the implications would extend far beyond particle physics. It would be the first direct evidence of the dominant form of matter in the universe. Astrophysics, cosmology, and fundamental physics would converge on the same question. What exactly is this particle, and is it responsible for all of dark matter, or only part? If evidence for extra dimensions appears, if gravity behaves differently at small scales, in ways consistent with higher dimensional theories, additional dimensions of space would exist. The universe would be larger, in a sense that has no parallel in any intuitive picture of reality. In each case, the discovery would not end science, it would begin a new era of it. Every answer in physics has historically generated more questions than it resolved. The discovery of the electron led eventually to quantum mechanics. The discovery of radioactivity led to nuclear physics, and then to the standard model itself. Discovery is the opening of a door, and behind that door, in every case, the universe has been stranger than expected. The confirmed discoveries of the past, the Higgs boson, quark-gluon plasma, CP violation, the behavior of the quantum vacuum, have each individually reshaped how physicists understand the structure of existence. Each one revealed that reality, at its most fundamental level, operates according to rules that nothing in ordinary human experience could have suggested. The next discovery, whatever it is, will do the same, and it will raise, more sharply than any before it, the question this entire series has been circling: whether the reality we experience is the whole story, or whether what CERN is finding, layer by layer, collision by collision, is the first evidence that there is something more, something beyond the frame of everything we thought we were looking at. That question deserves a full chapter. And it is the last one. We started with a loose cable, a fiber optic connection slightly out of position, introducing a timing error of 60 nanoseconds. Enough to make neutrinos appear to travel faster than light, enough to terrify physicists for months before the mundane explanation emerged. And then we asked, imagine what happens when the experiments actually work. Now we know. Does CERN alter reality? The conspiracy theory version of this answer is no. CERN is not shifting timelines. The Mandela effect is a documented property of human memory, a memory system that reconstructs rather than records, shaped by expectation, social reinforcement, and the gradual degradation of detail over time. The misspelled book series and the missing movie are evidence that human memory is fallible in specific and well-studied ways. The micro black holes have not swallowed the Earth, The strangelets have not converted matter into strange quark matter. The vacuum has not decayed. These outcomes were constrained by evidence from the cosmic ray record stretching back billions of years. The machine is safe. The world is unchanged in the ways that worried people most. But here is what is also true. CERN has altered our understanding of reality, fundamentally, repeatedly, and the alterations are not finished. The Higgs boson discovery confirmed that every particle of matter you are made of acquires its mass through interaction with an invisible field that permeates all of space. Your mass is not a property you have. It is something the universe does to you, continuously, through a field active since a fraction of a second after the Big Bang. The recreation of quark-gluon plasma confirmed that the matter you are made of was once a perfect, near-frictionless liquid existing at temperatures beyond any modern star, lasting for less than a microsecond at the beginning of time. The measurement of the Higgs boson's mass placed the universe in a category called metastable. Stable for now, but with a mathematical shadow suggesting the vacuum may not be in its lowest energy state. The detection of CP violation confirmed that the laws of physics are not symmetric in time. The universe has a preferred direction. The arrow of time is encoded, at some level, in the fundamental rules of particle interactions. The Muon anomaly suggests that something interacts with matter that the standard model does not account for. Something is there, influencing the behavior of particles in ways the best theory ever constructed cannot fully explain. Dark matter, which makes up 85% of all matter in the universe, remains undetected. It is real. Its effects are everywhere. What it is made of is unknown, and the constants of physics are fine-tuned to a degree that has no confirmed explanation. Does CERN alter reality in the way the internet fears? No, but it alters the reality of what we know. A shifted timeline would only change the story. What CERN changes is the frame, the understanding of what reality is at its most fundamental level, what it has been, and what it might become. Every run of the collider is a question. Every anomaly in the data is a thread attached to something larger, waiting to be pulled. The machine is still running, and what it finds next may change everything. Again.